So when we talk about what's a limit is how a function behaves as it gets very, very close to a certain point. And if you remember from your first calc class, you should know that there's two questions that you ask yourself about a function as x gets close to a. So as x gets close to a, does the function get close to some real number? And we call that number L, let's say. So if that question is yes, so as x gets close to a, the function gets close to L. And if we can make the function as close to L as we want by picking values very close to a for x, then the limit exists, and we use this notation. Let's see here, that didn't work out. Let's try that again. We use this notation. That didn't work. That's way too big. We'll use that notation to note that the limit as x approaches a of f of x is equal to L. Pretty straightforward. So what we're saying is as x approaches a, does the value of f of x approach some real number L? And we're going to keep in mind that it has to be a real number. And we're not talking about infinities here. So if you recall from previous classes, when you approach infinity, and we say that the limit equals infinity, technically that limit doesn't exist. Okay? So we'd ask ourselves two questions if we're looking at this. One, as x approaches a, does the function approach some number L? Yes. Okay. And can we get as close to this number L as we want by picking numbers that are very, very close to a? Answer to that question here is yes, we can get as close as we want. And so the limit as x approaches a of f of x here is L. Everybody good so far? All right. Somebody's going to remind me, what's the first thing you should always do when you're trying to evaluate a limit? Oh, I got to look at the chat. Let's see. Plug it in. That's right. So Nick says plug it in. Always just plug it in first. And if you have a function that is continuous at a, when you plug it in, you're just going to get some number. That's your answer, and you're done. So if you look at something like the limit as x approaches 4 of 2x minus 3, that function is continuous for all real numbers. Therefore, it must be continuous at 4. When we plug it in, we ought to just get a number, and we should be done. So what should it be? This should just be 2 times 4 minus 3, be 8 minus 3, or 5. Easy enough. All right, what about the next one? Next one, first step for our limits is always just plug it in. Plug in your -3, see what happens. You got -3 squared plus 1 gives you 10. You got some number, means you're done. Easy. This function, root x plus 2, is not continuous for all real numbers, but when we plug in 7, we still just get the square root of 9. We still just get 3. We still just get a number, so we're done. Easy. The function is continuous at x equals 7, even though it's not continuous for all real numbers. Everyone good? All right. We can see it graphically, right? On the graph, if we're looking at the limit as x approaches 1 of a function like x plus 2, we can see that it's hitting this point right here. It's hitting 3. The function is continuous. Just plug it in. 1 plus 2 is 3. Okay. So now we're going to have to look at the cases where this doesn't just come out to be a number, because if they all just came out to be simple numbers, life would be easy. This class would be easy. So we're going to look at this one. We've got g of x, which is x squared plus x minus 2 over x minus 1. What this graph looks like is just, it looks like the function x plus 2, like in the previous problem, except it has a hole at x equals 1. And we can see that it has a hole if we want to factor this. Factor the numerator, you get x minus 1. You get x minus 1 times x plus 2. And you get x minus 1 in the denominator. You can see the x minus 1s cancel out. That's what gives us the hole. So the questions we still need to ask ourselves are, 1, can we get as close to some value. In this case, it looks like that value is 3. Can we get as close to 3 as we want to by picking numbers closer and closer to 1? And the answer is yes. If I want to get y equals 2.9999999, well, that's no problem. I just have to pick a number that's very, very close to 1, just a very small amount less than 1. So we should see that this limit here is still 3. We can see it by canceling out the x minus 1s and then plugging it in, or we can just see it graphically. We see that there's a hole there, but the function's still approaching that value. Even though the function is undefined there, the limit's still 3. Good or no? Any questions? All right. All right, so now we're going to turn this into a nice, simple, easy, piecewise defined function. So it's the same as before, x squared plus x minus 2 over x minus 1, as long as x does not equal 1. Okay? But when x equals 1, the value of our function is going to be 2. What's the limit here going to be? Yep, Luke, you are right. It's still going to be 3. The reason is it doesn't matter what the value of the function is. All that matters is what we get close to as we approach x equals 1. And what are we getting close to? We're getting close to that hole that occurs at y equals 3. Doesn't matter that as soon as we get to 1, the function jumps down to 2. Does not matter at all. All that matters is we're getting very close to 3, and that we can get as close to 3 as we want by picking x values very close to 1. Everybody still good? All right, so the thing I want you to note is that for all of those functions, the limit as x approached 1 was 3, but for the first one, f of 1 was equal to 3. In the second one, g of 1 did not exist. And in the third one, h of 1 was equal to 2. So the main point here is it doesn't matter what happens at the point, right? It matters what's happening as we approach that point. As we look at a very small scale, very, very shrunken down version of this graph, very close to x equals 1. And that's what calculus is all about. It's about looking at what happens as we approach values, as we get very, very close to x equals 1 or some other value. Everybody good still? All right. So if we don't know what the value sitting there is, because on this one, it's, it's hard to tell. Maybe it looks like it's about 1.5 for that limit as x approaches 2. Maybe it's 1 1/3. Maybe it's 1 1/4. It's hard to tell. What's one method that we can use to solve these limits where we have holes at the value we're looking at? How can we go about finding this limit? Factor. Yep, Molly, that's right. One way is factoring. And the reason we'd see that we need to factor it is because if we plug in the 2 like we're supposed to, when you plug in 2 here, you get 2 cubed, which is 8, minus 2 times 2 squared, which is also 8, over 6 minus 6, right? We get 0 over 0. And what is 0 over 0? That is an indeterminate form, right? So we'll remember that 0 over 0 is indeterminate. What are the other indeterminate forms you talked about last year, Sam? Yeah, we talked about infinity over infinity. I don't know if, did we talk about any other ones? I can't remember if we did. Briefly, I probably mentioned they existed. Yeah, so we're going to talk about a bunch more when we get to really talking about L'Hopital's rule again. So hopefully you all remember L'Hopital's rule, but when we get to that, we're going to talk about indeterminate forms like 0 times infinity, 1 to the infinity, 0 to the 0, stuff like that. We'll deal with all of those. So 0 over 0 is our main indeterminate form, which means we can just factor out. Like Adrian said, we should factor out the x squared on the top and the 3 on the bottom. So let's do that. Remember that when you are writing these out, you need to include the limit as x approaches 2 at the beginning of it until you plug that 2 into your simplified equation. So we got x squared times x minus 2 over 3 times x minus 2. And the x minus 2's we can cancel out, giving us just the limit as x approaches 2 of x squared over 3, which now when we plug in that 2 gives us 4/3, and we can see exactly what that limit is. Everybody good there? All right. You guys do this one real quick on your own, and then I'll write it up here in a sec. So what's the first thing you should have done when you were trying to find this limit?
Plug it in.
Plug it in. When you plug it in, what do you get?
Indeterminate form.
You get indeterminate. You get 0 over 0. Perfect. So
Yep.
all we got to do is go through and factor it out. And so when we factor this out, we end up with the limit as x approaches 2. What did the top factor 2? Should have been x minus 2 times 2x plus 1. Oh, sorry, 2x minus 1. And in the denominator, it should have been x minus 2 times 5x plus 3. Everybody agree with that? Cancel out the x minus 2's, and now we can plug that in. Numerator becomes 3, denominator becomes 13. Simple enough? Okay. What about something like this? We got two different ways without using L'Hopital's rule that we could deal with this one after we test when we plug in 9 to see that that's 0 over 0, right? That's indeterminate. So once we've done that, what are the two different ways we can deal with this one?
Negative conjugate.
Okay. One is the conjugate, and what's the other one? Yep, Alice, that's right. The other way is we just use this as a difference of squares, or yeah, Molly, factor out the x minus 9. So we'll do both ways. We'll do the conjugate way first. So we got a radical x minus 3. If we multiply top and bottom by the conjugate of that, we should end up with the limit as x approaches 9 of x minus 9 times root x plus 3 over root x minus 3 times root x plus 3. And the root x minus 3 times the root x plus 3 gives us an x minus 9 in the numerator and in the denominator, which we can then cancel out. Leaving us with just the root x plus 3, plug in the 9, we can see that that's 6. The other option is simply just factoring it right at the beginning. So the x minus 9, we can see that x is square root of x squared, and that 9 is 3 squared. So that's really just a difference of squares. So we can just right off the bat factor the numerator to root x plus 3 and root x minus 3 over root x minus 3. Cancel them out, and you still get 6. Everybody good with that? Any issues there? All right, what about this one? First thing we should do is what?
Plug in
plug-
1.
Plug in 1. What do you get if you plug in 1? You get a half minus a half over 0. So you get 0 over 0. Okay, so what should we do then, now that we know it's indeterminate? Anybody? Molly, what do you mean by separate the terms in the numerator? I see what you mean. Molly, no, that's not going to work because that's just going to give us a half over 0 minus a half over 0. Luke, yeah, we want to simplify it down. And the way we simplify it down is what Adrian just said afterwards, is to combine them together and then we flip it. So don't necessarily have to flip it, but we can combine the two fractions in the numerator together and we can combine the denominators together. So let's take a look at the common denominator of the two fractions in the numerator. It should just be x plus 1 times 2. So we're going to get a common denominator up there. So we're going to get a 2 over 2 times x plus 1 if we multiply the first fraction by 2 over 2. And then the second one, we're going to get a minus, and then it's going to be x plus 1 over 2 times x plus 1. And all of that's going to be over x minus 1. So now we got the common denominator in the numerator. We'll combine the terms in the numerator. 2 minus x, and then 2 minus 1. So what's that going to give us? That's going to give us a 1, a positive 1, and a minus x up there over 2 times x plus 1. And if I have 1 minus x over 2 times x plus 1, all over x minus 1, what happens to that x minus 1 that's in the denominator of the bigger complex fraction?
Cancels out.
What's that?
It cancels out, right? No, we're not.
I can't hear what you're saying, but Adrian said something here. We're gonna combine them together. So like you can make that over 1, and it's a fraction over a fraction. You just flip them and multiply. So effectively, that x minus 1 just ends up in the denominator, the same denominator with it. Then what? What can I do then? Because at this point, nothing cancels, right? If I try to plug in 1, I'm still going to get 0 over 0. So how do I make something cancel? Yep, Ryan, that's right. Factor out the -1 that's in the numerator, or we could factor a -1 out of the denominator. It doesn't really matter. Take a negative out of the top, giving us negative parentheses x minus 1. And then we got our 2 times x plus 1 and our x minus 1 in the denominator. Now we can cancel out those x minus 1s. And we end up with -1 over 2 times 1 plus 1. So we end up with -1/4. Any issues with that? Any questions on that? Looks like we're going to need to do a few more of those at some point. I'll make sure to put some of those in the problem set I gave you guys. All right, let's move on. We're going to quickly talk about left and right hand limits. We'll remember that there's just a slightly different notation there. Left hand limit from the left with the negative sign in the superscript there, and the plus sign in the superscript means from the right or a right-hand limit. So when we talk about a limit, in order to have a limit that exists, a two-sided limit that exists at a point, we have to have an open interval on both sides of that a value that we're approaching. Well, for a left-hand limit, we only have to have an open interval to the left of that a value. And for a right-hand limit, we only have to have an open interval to the right of that a value. Okay? We don't care what's happening to the right if we're looking at a left-hand limit, and we don't care what's to the left if we're looking at a right-hand limit. Okay? Other than that, the same rules apply. We have to be getting closer and closer to some real number value of L from one side or the other in order for that limit to exist. Everybody good with the basic idea of a left-hand and a right-hand limit? All right, so if we're thinking about a function like the square root of x minus 2, I'm going to do my best to draw that here, something like that. And we want to find the limit as x approaches 2 from the right of f of x. We first have to think, do we have an open interval to the right of f of x? And what's the answer to that? Do we have an open interval to the right of it? Yes, we do. To the right of x equals 2, we've got function going on there. We've got an open interval over here, which means we can approach 2 from the right. And what value of the function do we approach as we approach 2 from the right? Should be getting closer to 0. Exactly. What about from the left? So in order to have a left-hand limit, we need to have an open interval to the left of x equals 2. So we have an open interval to the left of x equals 2. Here's x equals 2. Is there an open interval over there to the left? No, there's not. So we'll say this does not exist. And in order to have a two-sided limit, the limit as x approaches 2, we have to have an open interval on both sides. Since we don't have an open interval to the left, we'll also say that this limit does not exist. Okay. Which should lead us, I think, to an important rule that we probably know and remember, but that the limit as x approaches a of a function, the two-sided limit, can only exist, it can only equal L if and only if both the left-hand limit and the right-hand limit both exist and equal the same value. Okay? So in the one we just did, the right-hand limit existed, the left-hand limit didn't, so the two-sided limit can't. Vice versa, if the left-hand limit exists and the right-hand limit doesn't, we can't have a two-sided limit. And if they both exist but are different values, then that means we're not approaching the same thing from both sides, and we can't have the two-sided limit. Everyone good with that? So let's take a look at this one. If you remember the function absolute value of x over x, or ones like absolute value of x plus 1 over x plus 1, those are ones that often pop up on the AP test. You probably didn't see it last year because you had the shortened version. They usually show up in the multiple choice. So this year I'd expect to see something like that, assuming we go back and actually take the test in person. You're going to want to know what these graphs look like. So if I have absolute value of x over x, it's just a horizontal line to the right at x equals 1, starting at x equals 0. Oh, sorry, at y equals 1, starting at x equals 0, and a horizontal line to the left at y equals -1, starting at x equals 0, with open circles on both sides, because if I try to plug in 0, we end up with 0 over 0. So we should be able to do this, all three of these limits graphically, and we should be able to use the definition of absolute value to do all three of these limits algebraically. So first we'll do it graphically. As we approach 0 from the left, what is the value of my function? What's the limit as x approaches 0 from the left? Should be -1, right? Yep. And what about as we approach from the right? It should be 1. Exactly. So does the two-sided limit exist at x equals 0?
No.
No, this does not exist. All right, now what if we wanted to do this algebraically? Anybody have a good idea on how we could figure that out? We didn't have the graph in front of us, forgot what the graph looked like. The problem explicitly said solve it algebraically. What could we do? Anyone? Okay, so let's see, Ryan, we got separate the domain into two different functions, and Molly said plug in a number close to 0 from the left and the right. Okay, so yeah, so Ryan, what we're going to do, as you said, to separate into two different functions. Molly, just plugging in a number close to 0 from the left and right can tell us what's going on, but it's not an actual algebraic solution to it. So what we want to do is we want to use the definition of absolute value and actually rewrite the function absolute value of x over x. So if we're approaching 0 from the left, we have to think about what does that tell us about our x values. It tells us if we're approaching from the left that all of the x values are negative. They're all less than 0. And so if x is less than 0, what does that tell you about the absolute value of x? It's always equal to the opposite of x, right? If I plug in -5 and try and take the absolute value of -5, I get the opposite of -5. I get +5, right? So anytime you're taking the absolute values of negatives, you get the opposite of what you put in. So effectively, this tells us that the limit as x approaches 0 of f of x from the left is equal to the opposite of x over x. And even though that's still 0 over 0, we can cancel out the x's, turn that into the limit as x approaches 0 from the left of a constant, -1. And we know that the limit of a constant is always the constant. So this should just be -1. Everybody good with that? Algebraically, we see how to do that? Cool. All right. What about the other one? As x approaches 0 from the right, what is that telling us about the x values? All the x values should be greater than 0. And if we're taking the absolute value of a positive number, it comes out the same. It comes out to what you already plugged into it. So the absolute value of x is x when x is greater than or equal to 0. In this case, we're only worried about being greater than 0. So that tells us that the limit as x approaches 0 from the right of f of x is just equal to x over x, or the limit as x approaches 0 from the right of 1, which is just 1. So either way, we're going to get -1 and 1 and show that the two-sided limit doesn't exist. Everyone good there? Any questions, any issues on anything so far? All right. Let's do one more sort of similar to this, and then we're going to move on to some of the rules for limits that we're going to need to know. So let's graph this piecewise defined function. It shouldn't take you too long to graph this. And on a separate note, is it helpful for you guys to have the lectures recorded and have them up there? Has anybody actually gone back and like looked at parts of it or watched it again? Yeah, okay. All right, cool. Just making sure. All right, so 3 minus x for x less than 1. So we'll give ourselves an open circle here, and there's my best attempt at a linear function on my laptop screen. When x is at 1, we end up with 4. And when we're greater than 1, we should be looking at x squared plus 1, which is the right half of a parabola there. So it kind of looks like that. Hopefully that's what your graph looks like. What's the limit as x approaches 1 from the left? just by looking at the graph. As x approaches 1 from the left, we're getting closer and closer to 2. Exactly. So we'll say that's 2. What about the limit as x approaches 1 from the right? Are we getting closer and closer to some value? Should also be 2. And based on the rule we have from before, if the limit from the left is equal to the limit from the right, then it's just the same for the two-sided limit, we get 2. And if we were trying to do it algebraically, which piece of it would we look at for the limit as x approaches 1 from the left? Would we look at 3 minus x, or would we look at x squared plus 1? Should look at the 3 minus x, so we could say this is the same as the limit as x approaches 1 from the left of 3 minus x, which is 2. And for this one, we would say the limit as x approaches 1 from the right, and we'd use the x squared plus 1 part, which still gives us 2 for the from the right part. Then the only way to actually tell the two-sided limit is we can't use either of these. We'd actually have to use both of them, or just have done them separately for the one-sided limit. 1 second, everybody. I gotta help my son with something real quick. All right, sorry about that. He's just very excitedly telling me that he doesn't have any homework to do today. So, all right. The limit of a constant is the constant. We should know this. It's something from last year, something I've already briefly mentioned, something that you could probably find me saying online over and over and over and over again until you've lost your mind if you went on YouTube and looked for it. The limit of a constant is the constant. Okay? So the limit as x approaches 3 of 7 is 7. The limit as x approaches negative 4 of 10 is 10. The limit as x approaches 1,000 of pi is just pi, right? The limit of a constant is always just the constant, which should make sense because we're talking about the function 7 or the function 10. What is that? It's just a horizontal line, right? And so anywhere I go along the x-axis to, approach 3 or approach 1,000, I'm still approaching this same value. It's still just this horizontal line. Easy enough? All right. Some other important rules that we should know. I don't know why I've got these sort of out of order here, but the addition one, we can take two functions that we're looking for the limit of and combine them together as one, or we can separate one big function that's being added together as two separate limits. Same with multiplication, same with division, and for some reason subtraction's at the bottom, but same with subtraction. Okay. The only caveat there is that with the division one, the one in the denominator can't be 0 because obviously we can't divide by 0. Probably remember using this stuff a little bit with trig functions last year. We're going to do it again with some more trig functions this year. Then this one is another important one, which seems really basic and simple, but that if you have a constant times a function, so if I have the limit as x approaches 3 of 5, tangent squared x, that's the same as 5 times the limit as x approaches 3 of tangent squared x, right? So we can take the constant and pull it from the inside of the limit out to the front of the limit. And we used that idea also when we were working with integrals and converting from Newton's notation into regular Leibniz integral notation. So we'll see that again this year too. Everybody good with those 5 rules? Everybody, those look familiar to everybody, hopefully. All right, we can do the same thing with a power that's attached to a function inside of a limit. And this one we used a ton with trig functions. So if I have a power or a function being raised to a power, then I can take that exponent, take that power and move it outside of the entire limit, just evaluate the function within the limit and then raise the result to that same power of n, or whatever that power happens to be. So even though it doesn't really matter and make this any easier right here, I can take this limit as x approaches 2 of 3x plus 4 to the 5th power and make it the limit as x approaches 2 of 3x plus 4 and raise it to the 5th power. And hopefully later today, may not be today, maybe tomorrow, we'll do this with some trig functions. All right, but before we can do that, we got to talk about the sandwich theorem, or the squeeze theorem, which you hopefully remember. 1 second, I got to answer my kid's question again. So take a look at the picture and remember what that is from last year. All right, sorry about that. Okay, so sandwich theorem or squeeze theorem is a way we can evaluate limits of functions that are hard to evaluate, as long as we can find a function that is always greater than or equal to the function we're interested in, and another function that's always less than or equal to the function that we're interested in. And as long as those two functions both have a limit that is the same at the value we're interested in the limit of our function. So if we're trying to find the limit as x approaches a of h of x, we need to find a function that is always greater than h of x and a function that is always less than f of x. And we need both those functions, g and f, the greater one and the lower one, to have the same limit at a. And if they have the same limit at a, then the function that's sandwiched between them should also have the same limit at a. I think just looking at the picture kind of makes it make sense. Like g is always greater than or equal to h. F is always less than or equal to h. And the limit as x approaches a of f and g are the same. So the one that's sandwiched between them has to have the same limit. Does that make sense to everybody? Does that sound familiar to everybody? All right. So let's use that theorem to prove that the limit as x approaches 0 of x squared sine 1 over x squared is equal to 0. And we're going to do that right after we look at the graph. I know for those of you that were in my class specifically last year, you should have seen graphs of something similar to this. I don't know if we did this exact one, but this, that's not it. There we go. So x squared sine 1 over x squared. You guys can see it on Desmos now, yeah? Not just the lecture notes. You guys can see Desmos, yeah? All right, cool. Yeah, I've turned off all of your faces so they don't show up in the video when I post it. So I can't, if you're just nodding your heads, I can't see. Just unmute yourself and say yes, or type it in the chat, and I know, but we're good now. All right, so here's x squared sine of 1 over x squared. So what we're looking for is we're looking for a function that's always above this and another function that's always below this that have the same limits at x equals 0. And so if we can find that, if we can find two functions that satisfy those conditions, then we can know what the limit of this function is. And so the way we go about this is what? Somebody remind me how we go about this. What do we know about the function that's inside of here? Let's say the sine of 1 over x squared without the x squared part. Tell me what you know about the sine of 1 over x squared. Okay, yep, Alice, exactly. It oscillates back and forth between -1 and 1, right? Because we know that anytime, 1 over x squared is just some number, right? No matter what x is, as long as x isn't 0, which it never will be because we're approaching 0. 1 over x squared is just a number. We take the sign of any number, and that ends up between 1 and -1. And so what this effectively does is it gives us the starting point of our sandwich theorem, right? We don't quite have our function in the middle, but we can take the x squared that we need to have with it and just multiply it by everything and get -x squared is less than or equal to x squared sine 1 over x squared is less than or equal to x squared. And if we go back and take a look in Desmos and throw in our x squared and a -x squared, we can see that very clearly that our x squared function is an upper bound for x squared sine 1 over x squared, and -x squared is a lower bound for it. And you should very quickly be able to know exactly what the limit of x squared and -x squared as x approaches 0 is, right? The limit as x approaches 0 of -x squared is 0. And the limit as x approaches 0 of +x squared is also 0. And so by the sandwich theorem, that tells us that the limit as x approaches 0 of x squared sine of 1 over x squared also has to be 0. Does that make sense to everybody? I know we did those if you were in my class last year, but for the couple of you that weren't in my class, that's all good. Nice little handy use of the sandwich theorem. What about this one? Similar concept, except with cosine. What do we know about cosine? Same thing, right? Cosine of 1 over cube root of x ought to oscillate back and forth between +1 and -1. And we can throw in this x to the 4th just by multiplying all the pieces by x to the 4th. And looking at the limits as x approaches 0 of -x to the 4th, which is 0, and the limit as x approaches 0 of +x to the 4th, which is also 0. And so once again, by the squeeze theorem or the sandwich theorem, this one is also equal to 0. Everybody good there? Madhavi, I know you asked me this question. Yeah, you don't need to use a proof to explain how you went about solving it. Nope. No proof needed, just we know what the sandwich theorem is, and so stating that you used it is good enough. One issue that we might come across at some point is that, you know, what if we had an x cubed in front of here? We're not going to do one with this, but what if we had an x cubed in here? That creates a little bit of an issue. What's the issue that creates? So if this was x cubed cosine 1 over cube root of x. Right, exactly, Adrian. So when we multiply by x cubed, sometimes x cubed is positive, and that's not a problem. But sometimes x cubed is negative, and that creates a problem because we've got an inequality. So if we're multiplying by x cubed, or anything that could possibly be negative, we have to separate it into the different cases. One where the value that we're multiplying by is positive, and one where the value that we're multiplying by is negative. And then because of that, we'd end up having to do some one-sided limits, but we're not going to stress too much about that. I don't think you'll end up seeing anything like that on the AP test, but just keep in mind that the reason this worked out so nicely is because these were positives. If these could have been negatives, you got to do a little extra work and separate it into two different cases, one where it's positive and one where it's negative. All right, So now we're going to use the sandwich theorem to prove this limit that you should already know. We should know that the limit as x approaches 0 of sine x over x is 1. It's just one that you should have memorized from last year. If you don't have it memorized, that's fine. You will memorize it. But that's the problem. All right, that's what it looks like, sine x over x. And we can see that it certainly looks like it's approaching 1 as x approaches 0, even though there's a hole in the graph there that Desmos doesn't show. Nothing weird's going on. It is approaching 1. Question is, how can we use the sandwich theorem to prove that? Any thoughts or ideas about how we can do that?
Can't you go about solving it the same way we did with the last problem, where we set it up where negative sine is less than or equal to sine is less than or equal to positive 1, and then afterwards divide both sides, like the negative 1 and the 1, by the x, and also the sine? Does that make sense?
You're saying take sine x is less than or equal to 1, greater than or equal to negative 1, and then divide them all by x?
Mm-hmm.
So it's a good idea, but unfortunately that's not going to work out because we're looking about as x approaches 0, right? And as x approaches 0, these would all have this one and this one would have to have the same limit. But as x approaches 0, what's the limit of negative 1 over x and 1 over x?
So it'd be indeterminate. Never mind.
Yeah, it's not indeterminate. It's undefined, right? Here's 1 over x. As x approaches 0, from the left-hand side, it's going down to negative infinity. And from the right-hand side, it's going up to positive infinity. And vice versa with negative 1 over x. From the left-hand side, it's positive infinity. And from the right-hand side, it's negative infinity. 1 second. So Adrian, you said use the areas of the triangle. You must remember vaguely what we did last year. So let's get rid of all this stuff that we got here and start this over again. So what triangles are you talking about, Adrian? So this one in yellow right here that's on the inside. And let's see, how about, the big one here on the outside, that's the red one. And we're gonna have to use another thing too, because if we're talking sandwich theorem, we gotta have 3 different pieces to this. So let's talk about the sector of the circle that we got there that I'm sort of outlining in blue. What can I label on here already? So let's call this thing a unit circle. And if we call it a unit circle, then we know what this length is, right? What's that length if this is a unit circle? Should be 1, okay? And what about this length up here? Should be also 1, okay? And then what about this height right here? If this is, let's say this is angle x, then this upper one here is the y value, so this should be sine of x. And what about this little piece here? That should be cosine x. Okay. All right, good. Off to a good start there. So can you tell me what is the area of the triangle that I drew in yellow? Yeah, the area of the triangle in yellow should be the height, sine x, times the base, 1 divided by 2, sine x over 2. So hopefully, can you guys see the yellow okay? Is that all right? I know it's hard in the classroom, but here it's probably okay. Okay. What about the red triangle? What is this height of it? We know that the base of it's 1, but what's the height of it? Why is the height of it tangent to x, Adrian? You're not sure. Okay, well, think about it. If we are looking at this little triangle on the inside, what's the opposite over the adjacent here? It should be sine x over cosine x, which is tangent x, right? It should be tangent x. Well, out here, it should be the same thing. It should be opposite over adjacent should be tangent x, and the opposite is what we were looking for. The adjacent is just 1, so the tangent of this angle should be opposite leg divided by adjacent leg, which is tangent x divided by 1. So what's the area of that red right triangle? It should be tangent x over 2, or 1/2 tangent x. Everybody good so far? All right, what about the blue sector of the circle? How do we find the area of the sector of a circle? It's just the fraction, it's the angle, the theta out of the 2 pi of the full circle times what? Times pi r squared, right? It's the full area of the circle times the fraction of the circle that we have. Well, our theta is just x, right? So in our case, this is x over 2 pi times pi r squared. What's our r value? Our r value is 1, so r squared is just 1. Pi's cancel, and so the area of the sector of that circle is just x over 2. Everybody agree with that? Any issues with that? Okay. So what is the point of all this? Why do we do all of this? What can you tell me about this yellow triangle? Yeah, we could set up an inequality, exactly, Alice. This yellow triangle has to have a smaller area than the sector of the blue sector of the circle, right? So sine x over 2 must be less than or equal to x over 2. And the sector of the circle must be less than or equal to the big triangle that extends outside of it, right? Exactly. Yellow is less than the blue is less than the red, Adrian, exactly. And so now we've got an inequality that definitely does not have sine x over x in the middle of it, but I can turn x over 2 into sine x over x pretty easily. First thing I can do is I can just eliminate all of these over 2s. So those are just waste of space. That's just extra stuff that we don't really need. And then from there, how about we divide everything by sine x? So let's make this sine x over sine x is less than or equal to x over sine x is less than or equal to tangent x over sine x. And when we divide by sine x, we're going to just assume that we're working in the first quadrant here. And we can do some work to extend this proof, this theorem, to any real angle, but we're not going to bother to do that today. We're just going to assume we're working in the first quadrant, and the first quadrant sign is always positive, so we don't have any effect on these inequality signs. But if we wanted to pick a sign that was in a different quadrant, not the first or second, but in the third or the fourth quadrant, we could separate this into multiple cases and still prove that it's true. So, the first one, sine x over sine x, ends up becoming just 1. So we got 1 is less than or equal to our x over sine x, and our tangent x over sine x should simplify down to just become what? yeah, secant x, 1 over cosine x or secant x, either way you want to write it. Doesn't really matter. Let's leave it as 1 over cosine x, I guess. Doesn't really matter. And then in order to turn sine x, or x over sine x into sine x over x, what do we need to do? We just need to take a reciprocal. And anytime you take the reciprocal of something, of all the sides in an inequality, the inequality signs have to flip. So reciprocal of 1, flip the inequality sign, reciprocal of x over sine x, flip the inequality sign, and reciprocal of 1 over cosine x or secant x gives us just cosine x. And from there, we're pretty much done. What's the limit as x approaches 0 of 1? It equals 1. And what's the limit as x approaches 0 of cosine x? Well, it's the cosine of 0, which is 1. And so now we've got the limit, the left-hand function, or the function that's always greater than or equal to sine x over x has a limit of 1. And the function that's always less than or equal to sine x over x has a limit of 1. Therefore, the function that's sandwiched in the middle, the limit as x approaches 0, sine x over x also has to equal 1. Good? Any questions or issues with that? Now, I know it would have been a lot easier if we just used L'Hopital's rule to solve that, but it's way more beautiful this way. So I think we got a few more minutes. What time do we get out of here? Like 10:04 or something like that? We got about 10 minutes left. Does that sound right? At some point, I'll actually know what the schedules are. So let's see if we can apply this to a couple quick, simple, easy limit situations. So now that we know that the limit as x approaches 0 of sine x over x is just equal to 1, we should be able to figure out what the limit as x approaches 0 of sine 5x over x is. All we have to do is turn the argument of the sine and the denominator into the same value. So we're going to multiply the top and the bottom by 5 over 5, or multiply the top and the bottom both by 5, so effectively multiplying the whole thing by 5, giving us 5 sine 5x over 5x. And this constant, this 5 that's sitting inside of here, can get pulled out. And just to start off with here, we're going to prove that sine 5x over 5x, its limit as x approaches 0 is also 1. And how we can do that is we can make just a real simple variable substitution. So if we take the 5x and get rid of it, we'll call u equal 5x. So if u equals 5x, this is going to give us 5. This is going to give us a sine of u over a u. And if u is equal to 5x and x approaches 0, then what is u also approaching? It should also approach 0. So this really just effectively becomes a limit as u approaches 0 of sine u over u. And this we should know is equal to 1. We get 5 times 1 equals 5. And pretty straightforward. From now on, I'm not going to ask you to do this actual variable substitution. Anytime it's sine 5x over 5x, just know that's 1. If it's the limit as x approaches 0 of sine of 12x to the 8th over 12x to the 8th, still just going to be 1. Okay? Yeah, there you go. So I already answered your question, Nick. Everybody good with that? Everybody feel like they could do that? All right, let's do 1 or 2 more of these and I'll let you guys go. And then we'll pick back up and hopefully get through the second half of all of this tomorrow. We'll be pretty much done with limits. So we got the limit as x approaches 0 of sine cubed 4y over y cubed. So first off, what do we notice is going on in both the numerator and the denominator? Oh, this should be a y. I keep forgetting to change this. Got to get my variables straight. That's a y, not an x. All right. So what do we notice is going on in both the numerator and the denominator of this? Both have a cubed, right? Both are to the 3rd power. So we can take that power just like we were talking about with some of those rules on limits earlier. Y approaches 0 of sine 4y over y, all of that cubed. And then if we can get both the argument of the sine and the denominator to look the same, we should be able to very quickly evaluate this. So we multiply the denominator by 4 to turn it into a 4y, and we multiply the numerator by a 4 to turn it into 4 sine 4y. We still have cubed up there, so when we pull this constant of 4 out and put it in front of our limit, we're not really just pulling out a 4, we're pulling out a 4 to the 3rd power, or 64. So this ends up being 64 times the limit is y approaches 0 of sine 4y over 4y, and the cubed that's around the sine 4y over 4y can be applied outside of the full limit. Now this limit inside of here is just 1, so we've got 64 times 1 cubed, or just 64. Everyone good with that? Any questions on that? All right, last one. We'll stop after this one. So here we got a little bit different situation because our sine is being raised to the 4th power, but our z in the denominator is being raised to the 12th power. Good news is what we need to have in the denominator is actually a z cubed, and z cubed to the 4th is z to the 12th. So we can pull the 4th power out of this still, giving us the limit as z approaches 0 of sine 3z cubed over, and we might as well pull that 1/4 out here now, that 4 that's in the denominator. And this becomes a z cubed, and all of that is raised to the 4th power. Everybody good with that? Okay, so then we'll just throw in a 3 in the denominator and a 3 outside the sign in the numerator. Pull out the 3 to the 4th power. 3 to the 4th power is 81. So we got 81/4 times the limit as z approaches 0 of sine of 3z cubed over 3z cubed. And all of that is being raised to the 4th power for the limit, which gives us 81/4 times 1 to the 4th power, or 81/4. Any questions or issues with that or anything we've done today?